I want to talk about asymmetric public-private key encryption in OpenSSL and Node.js. I don't want to spend too much time on the big picture, Bob and Alice and message, blah, blah, but I will because I don't know if you've heard it before, and there are some important points that aren't hit on in the common diagram. So we have some person, Bob, and he wants to send a secret message to Alice. And so Alice has two sets of keys. One is a public key, meaning that everybody in the world, she posts it on her blog, on her website, she tweets it. Actually, there's a website that helps you do this, keybase.io, that helps you spread your public keys. And then there is a private key that she keeps safe, locked away in her heart, or at least on a computer that she doesn't let other people have access to and that has tight permissions on it. So an SSH key, for example, or an HTTPS key, which we'll get to in just a moment. But anyway, so Bob wants to communicate with Alice. Alice is like my bank in this situation, and Bob is like me. And so Bob gets Alice's public key, and he takes some message that he wants to send her. This is false. He's not actually going to send her a message with the public key, but for this example right now, we'll go with it. So he encrypts the message, and then he sends it to Alice, and then Alice decrypts the message with her private key, and voila. Now, to give another analogy of this that maybe will help you understand better, let's consider a safe, particularly like the kind that you might want to use at a 7-Eleven if you're the store manager. So you basically want anybody in the store to be able to lock the key at some particular time. They're probably going to lock it at like 7 o'clock or whatever it says on the sign outside the door, right? So you want them to be able to lock this. So they need a key that can make it not openable. And the manager wants to be able to unlock it, but she's going to come in the morning and unlock it and take the money and put it to the bank, and then it can stay unlocked for a little while, so it's easy to put the money in and out. But then at a certain time again, the public key in this situation is the store key. It's like any employee can use the store key to lock the box, but only the manager can use the private key, this master key, to unlock the box. So you can kind of imagine this mechanically. Hopefully that helps you understand it a little bit better in terms of, if it can be done mechanically, it can kind of also be done algorithmically, although perhaps in a different way. And it's kind of one of those tricks like this one, where you think of a number, any number, you multiply it by 2, you add 10 to your total, now divide your total by 2, finally subtract the total from the first number you picked, and your answer is 5, except instead of you thinking of a number and then subtracting that number away, it's this, you get this public number, and then the private number is what is able to decrypt the message. So it's similar to this, but obviously a lot more fancy and a lot more secure. And then also another interesting quality of this box is it's very, very small. In fact, it's so small that it can only hold maybe another key. So it's not quite big like this at all. It's a very, very tiny box. And it's also very arduous to open the box. It's a very slow process to unlock it. And then one other interesting property is that if you were to somehow you try to attempt to use the master key to lock it, instead like a light comes on, and then you can turn the light off by inserting the other, like the store key, and then the light goes off. And that's kind of like this idea of signing, which would also be similar to, you take a message and then you take something that's kind of personal about you and you sign the message. So in the case of The Simpsons, Matt Groening's signature is right there. So that's kind of the idea behind the encryption of the signature. Now let's go back to this. There's a problem with this example, because one, the box isn't big enough for Bob to fit his message to Alice. Well, in this case it is, because it's only hello Alice. But let's say that Bob was writing Alice an email. An email is actually too big to fit in this public-private key encryption lock system. And also, when Alice gets the message, we don't really know who the message is from. Like, we assume it's from Bob, but maybe it's not from Bob. Maybe it's from Steve, Or maybe somebody else submits a message and says it's from Bob, but there's no way to verify it. So we need to use the reverse system as well. So Bob would need to have some sort of authentication, either that he puts in the message, like he might say, "Hello, Alice, this is your secret admirer. The passcode is 3476, right? And he could encrypt that message, which is kind of like what happens when you sign into your bank. You actually, your browser isn't sending the bank its public keys because it doesn't have any public keys established, and they wouldn't, even if it had public keys, it wouldn't identify you authentically. But what identifies you authentically is actually what you put into the message to your bank, which is your username and password. So with this really small box, what we actually need to do is not send the message "Hello, Alice," but we need to send a secret code, because I'm not going to send every single message to my bank with its public key. And if I did, then I don't have a public key that my bank could send me back a message with my public key. And these messages are too large. They're images and they're web pages, and they're very large in consideration with how big this key is. So the key is tiny. What we want to pass instead with the key is an asymmetric, or with the encryption is an asymmetric key. So I think I talked about that somewhere. Anyway, I'll just skip ahead to this part, but let me finish saying that for a minute. So my web browser is going to come up with some number between 40 quadrillion, tillion, quazillion, and 41 quadrillion, zillion, billion, tillion, right? And it's going to send that number back to my bank, and then for the duration of my session with the bank, we're going to communicate using that number as a symmetric cipher. And I'll talk about that a little bit in the next blog post I do, fingers crossed. So one cool, interesting thing about the way that this works is that if I were to take the largest image on the internet, which is obviously XKCD's money poster, and I were to download it with curl, if I were to look in Wireshark and see the bits that come across the wire, obviously they'd be encrypted. But if I do it again, I get a completely different set of bits, because every single time I make this exchange through the RSA public-private key process, I choose a different random number, and I send that number back, and then for the duration of our session, we use that random number, which means that with curl, every single time I make a request, I'm actually reinitializing my HTTP session, or the HTTPS session, and I have a completely different random string of digits that I'm ciphering with. So let's put that on the table, talk about that later, and just look at the OpenSSL tools. So what I want to do is I want to make a couple of key pairs. So a private key actually also contains the public key. So I'm just going to make a directory for Bob. I'm going to create a 2048-bit key for him, which means that I could store 256 bytes of data, except there's also some padding and some metadata, so that wouldn't quite fit. And we're going to see something interesting in just a minute, so let me get out of that. So I make my key pair for Bob, generate the private key, and then I extract just the public key from the private key. And then I'm going to do this for Alice as well. Although technically, depending on the way I want to do encryption, if I'm doing it like HTTPS, then I don't need authenticity on the side of me because I'm authenticating with a username and password. If I was doing PGP, or GPG, where I'm sending messages back and forth over email, I do want both sides to have authenticity. I want to know that I am authentically Bob, Alice should know that, and I want Alice to be authenticated. I want to know that her messages, that she's the author of them, right? So I create those keys. If I was going to do this in JavaScript, I would need the ursa module, and it's pretty much the same thing. I generate a private key, I convert it to a text file instead of a bunch of bytes, and then I take the private key and I extract the public part from it so that I can share it with others. So if I go ahead and run this, by the way, if I just look at Bob, there's Bob's private key, there's Bob's public key. This is going to be a lot shorter because I only selected 1024-bit key right here. And then this number is just kind of a magic number. You can pick either 3 or this number or like 9 or something. I don't remember why, but they're just standard numbers to use as the second option. You can technically use a lot of them, but OpenSSL only uses a couple of them. And so I want this key to be compatible with OpenSSL, and I don't really understand it, so I'm just going with the default. It doesn't really matter. It doesn't make it more or less secure choosing a different number. It just needs a number there that's like either prime or odd or something. Anyway, so this is only a 1024-bit key. You can see it's much smaller, and then the public portion is much smaller also. In here is both the private part and the public part, and some metadata. Okay, so moving right along, if you wanted to do more command line style, this is what that would look like, where it actually creates the directory. So I have it create the directory right there, and then it actually writes out the files to the directory. So that's the only difference between these two. So now let's look at actually signing and encrypting data. So before, we don't, like I said, we don't actually want to, I am going to encrypt arbitrary data just so you can look at it as text instead of me having to have like an array of numbers to look at, which I guess isn't as cool. But what you would do is you would use PBKDF2 or a similar algorithm like bcrypt or scrypt to derive a key from a passphrase. You would encrypt that key, send it across the wire, and then, or you just generate it randomly if it's session-based like HTTPS. So you send it across the wire, and then when you want to sign, you don't sign the actual message, you sign a SHA-SUM. Remember that MD5 is now considered broken. There are some realistic ways in which MD5 is no longer secure. I won't go into those, but I mean, it's not like if you use MD5, suddenly you're vulnerable to lots of stuff. It's just that bits could get twisted in a file in a particular way, and although it would be benign, it would corrupt the file and you'd still get the same MD5 sum. Or if the person was really weird and they wanted to give you a file that did good things and bad things, they could give you both versions. You can look up the paper on it. Anyway, so if you want to understand a little bit better like the subtlety between signing and encrypting, because they're very similar, this Stack Overflow post has a little bit on it. And then if you want to see more of the OpenSSL commands that you do, this post right here has that. So I'm going to do a little bit in OpenSSL, and then I'm going to go back to doing it in Node. And I don't want to forget to say this. So you can think of the way that you might use RSA and AES keys together in the same way that you use video and audio together. So RSA, you could encrypt and then you could sign, or you can sign and then you can encrypt, or you could encrypt a key that you've signed and then send it, or and so just like you have MP4 and MKV and AVI and MOV and FLV, and they can all contain H.264. Every single one of these containers can have the data be H.264 for the video, and then have some auxiliary metadata, and maybe use MPEG style for the audio, or maybe use something else, but each of these containers can use that. And that's kind of the same with HTTPS and GPG and PKI and X509. Like, these are all standards that can use RSA or perhaps another public-private key pair system, and then that's for exchanging the symmetric key. And then for the symmetric key, they can use AES, but they might also use something else. And then the metadata, whether it's signing first or encrypting first, or how to do the padding, or how to do the concatenation in the binary format, that's all part of the standard. So we're not really going to talk about that. We're just going to talk about low-level RSA encryption. So one interesting thing is that RSA encryption actually does work, let me get out of here, on plain text, whereas AES encryption will not. You must derive the exact length of bits for an AES function to work. But with an RSA function, you don't necessarily have to, which is kind of interesting. The message size is, so AES, the message size is based on the size of the data. With RSA, the message size is based on the size of the key. So the signature is always going to be the same size as the key. Let me make sure I'm speaking correctly here. Yeah, so 256 bytes. Like every message can only be a maximum of 256 bytes, but there's padding, so it has to be less. And even if you're just sending the letter A, it's still going to be 256 bytes. Like that's how big the key is. That's how big a message must be. That's 2048 bits. If I was doing 1024 bits, then it would be 128 bytes. Anyway, so I went ahead and I signed that, and I signed it with, let's see, I was using Bob's private key, and I was putting out in the binary message.sig, and now I'm going to encrypt it, but I'm going to encrypt it with Alice's public key so that she's the only one that can read it. So now I have these 3 message files. Well, and I've got this other one that I was messing around with for some reason. Clear. All right, so I've got these 3. I've got my plain text, I've got my signature, and my encrypted bit. So if I want to verify the signature, I must have the plain text. I can't derive the plain text from the signature. But basically, it's kind of like if I take the plain text and I take the signature, that kind of produces the public key, more or less. Whereas if I take the public key and encrypt it, and then I get the encrypted with my private key, and I mix the private key and the encrypted data together, and then it reveals the text. So that's, again, you know, you could see different ways of combining these together for different protocols for different purposes. If you wanted to be anonymous, then you might encrypt the signature, you know, anonymous to everyone except for the person you're speaking to. But if you wanted everyone to know that, you know, you were an authentic messenger and that your message should have some priority, then maybe you want to be authentic. Anyway, so that's that. And we're going to look at it in Node, and we'll actually do the verification. So, and I do want to say, like, it is quite common for people to get confused and say to encrypt the private key. You cannot encrypt with the private key. It is only for decrypting. You can only encrypt with the public key. You can only sign with the private key. You can only verify a signature with the public key. But sometimes we think of private and encrypted as the same, but in this case, they're the opposites. So I think I'll just walk through this code and then I'll copy and paste it wholesale. Basically, all I'm doing is reading in the private key, reading in the public key, and honestly, I don't even have to read in the public key because the private key contains the public key. So here, I could have done privkeybob.toPublic key and called that instead. And maybe I'll update this to do that because that does make sense. It also makes sense to have it this way because yeah, it does make sense to have it this way because Bob has to have Alice's public key. Yeah, so it does make sense. So it actually, I've grouped these incorrectly because it should be Bob has his private key and Alice's public key. Those go together, and then Alice has her private key and Bob's public key, and those actually are what logically go together. And then this would be not a string message like an email, but it would be like the key that I want to encrypt to send my larger message with. So I'm going to send an email, I create some key, I encrypt that key with RSA, then that key is most likely an AES key, and then I encrypt my email with that key, and the signature goes in there somewhere as well. I forget how GPG defines it, but then I send that to Alice, and then when she receives it, then she's able to do the reverse process with her private key to decrypt and my public key to verify. I could even send her my public key with the message. Well, that wouldn't make sense because she would have wanted to get it from some source that she knows that it's actually me, because someone else could send a message that has a signature that or a public key they claim is my public key. So she'd want to get the public key from like my website or something like that. Or we've exchanged it earlier because we already trust each other. So anyway, let's see. Yeah, so I'm going to encrypt with her public key. I'm going to then, and in this case, I am just encrypting the plain text. And then again, I don't sign the actual message. Instead, I sign a hash sum of the message. So I'm getting a SHA-256 hash sum. The message is currently encoded as UTF-8. You can read the documentation for these parameters on the URSA website. And then there's base64 is the encoding that I want back. So let me just copy everything up to that point and paste it in and let you take a look. Boop, boop, boop. Oh, and I forgot that I actually need to change this variable name. Got to remember to do that. So this is inc. There we go. Instead of the plain text message. I did that somewhere else too a little bit later on. And then Alice is going to receive this message. She's going to decrypt it with her private key. She's going to verify that it's Bob. If the original message that I still have in memory doesn't match the new message, then I'm going to throw an error that it was invalid, which normally that error I think would happen at this process, but it is possible that you could actually decrypt a message that happens to match and it be the wrong message, I think. At least that's possible with AES encryption. I'm not sure that that's possible with RSA encryption. But if you decrypt with the wrong key, it could work. But of course, if you're not malicious, then you have the correct key, so you don't worry about that. And by work, I mean it could not throw an error. Anyway, so then I'm going to take the signature of my plain text message. I'm going to SHA-SUM it, and then I'm going to use Bob's public key to check against the signature that I already had, and then I will know. So now I'll do this part. Ta-da! And I should have done RCV there as well for the received message, but it turns out to be the same thing, so it all works. Anyway, so that's kind of how it goes. That's just a bunch of garbage I've already deleted. So hopefully that helps you understand a little bit better what RSA keys are used for, that they're not actually used for sending the messages or the files. They're simply used for transferring the keys and the signatures of the message and the files, because they're it's a very slow algorithm and you can only put a very little bit of data in it. But the symmetric keys are very, very fast, and they're block algorithms, so you can put lots and lots, as much data as you want, you can string through them. I think that we covered everything, except one thing that's not intuitively obvious to some people is the signatures not only verify authenticity, but it's also tamper proof. So if I go in and I change one bit in the message, whether it's encrypted or plain text, then the signature won't validate. So that's why you can, if you want it to be a public message, you can, or if you want it to be an encrypted message, you can. It doesn't matter. The signature is to validate authenticity and that it hasn't been tampered with. And then let's see if there's any... and then we talked about, HTTPS is you can start a two-way encrypted conversation with only one set of keys because you switch over to asymmetric encryption, whereas something like GPG, you would have two sets of keys because its authenticity is important in both. You can read through the article if you want. There might be some other interesting things in here. But I hope that helps your understanding, and it helps you feel more confident that you can do cool things with Node and OpenSSL for that matter. Okay, bye. If this was useful for you, please go ahead and give that little thumbs up button a nice click. Also, you'll see the notes are in the comments section down below. You can either at the end of the article or right up at the top. Give it a like, tweet, +1, whatever. Thanks.